Hi, everybody. Welcome back to the Quantum BC Seminar Series. We're continuing to have our last couple of talks in the summer. Today, we're hearing from Ulrike Stege, a professor in the computer science department, who runs an unreasonably popular quantum algorithms course here at UVic that's going on now, and I assume will go on soon. And she's going to talk to us today about her research in hybrid quantum classical algorithms.
Thank you, Thomas. Thank you for the invitation to speak at the seminar. I want to talk today about challenges when tackling solving of constrained combinatorial optimization problems. And as you have heard, I'm in the Department of Computer Science, so you're getting a computer science perspective here. So I want to start by talking about quantum utility for a little bit, and then give the context of the talk with respect to combinatorial optimization problems and with respect to classical complexity. And then I'll be talking about solving constrained combinatorial optimization problems via the QAOA, the Quantum Approximate Optimization Algorithm. And in the end, if I have time, I'll talk a bit more about research group activities going on. So the concept of quantum utility marks a critical threshold where quantum systems begin to deliver practical advantages over classical counterparts in solving real-world problems. And as such, quantum utility can be achieved by performing reliable computations at a scale beyond the classical brute force, or by quantum computers serving as useful tools to explore meaningful scientific problems. And of course, quantum utility is limited, for example, by the number and quality of qubits and on current devices, for example. One Qubit company in Vancouver that many of you may heard about or know, they used to have this banner on their website which says refine intractable, something that I always liked. And redefining intractable, that can mean to have a methodology that allows us to solve classically intractable problems better and faster. And as such, NP-hard problems, these are problems I want to talk about, for which we have good reasons to believe that polynomial time algorithms, and therefore the truly feasible solutions at scale, do not exist. They bring potential to demonstrate quantum utility. So the problems, NP-hard problems I want to talk about, they are combinatorial optimization problems, and they show up everywhere. They are in logistics, network design analysis, scheduling, data science, portfolio optimization, computation biology, you name it. You can find them in all application areas. And maybe in simple terms, the combinatorial optimization problem is a type of problem where you are trying to find the best option or a combination of options out of a large but countable set of possibilities. So that's a very generic definition of it. Now here you have a bunch of famous examples of combinatorial optimization problems. So I hope most people have heard about at least some of those. So for example, the traveling salesperson problem is a very famous one. Knapsack problem is another one. Knapsack, for example, can be helpful in portfolio optimization when you want to select assets to invest in while staying under a certain risk threshold, for example. There is a set cover problem, helpful in also software testing, for example, in logistics. Matching problems, they are particularly useful in resource allocation, minimum spanning trees in network design, maximum flow problems also in resource allocation, but they all have different areas as well. Maybe particular like independent set vertex cover and the clique problem. Let's put dominating set in this. These are all graph problems that have a lot of applications in bioinformatics, in data anonymization, in urban planning, dominating set in particular, etc. So there's a lot of applications of these problems. And again, many of you might have heard about the max cut problem if you ever read about QAOA before. So max cut is that problem that is used a lot with this technique. And if you look at these problems, I just listed their sum, of course. Many of these problems are NP-hard, and that's what I want to show with that. So for many of them, we assume there's no polynomial time scalable solution. And so the bold-faced ones here are all NP-hard problems. Matching problems, there are also some polynomial time problems, but there are many NP-hard variants. And so NP-hard problems, we can't escape from them. And so hopefully we can tackle them better. So working under assumption, again, that we might have to use, for example, exponential time, can't solve these problems in polynomial time. How do people tackle interactability? Well, one way, of course, is if you are working to solve instances for a certain problem, like knapsack or whatever, and for particular instances that have certain properties. If you know that, then you can design a particular algorithm for that and might be able to do that faster. Sometimes you can, sometimes you can't, depending on the properties. But there's some, if you have more knowledge, that can help a lot to be better and come up with scalable algorithms. You might say, okay, so we are happy to settle for near optimal solutions. Maybe it's best, maybe it's not, but it's good. I would be happy with that. But even that, for NP-hard problems is not always easy to do efficiently and with scalable approaches. Many NP-hard problems are hard to approximate. But then again, not all of these NP-hard problems are equally difficult to solve. The problems can be distinguished in terms of parameterized complexity in problems that are in the class FPT and problems that are likely not. In FPT, so what we do in this framework, we consider the problem and pick out a parameter. We look at parameterizations of these problems, and we design algorithms with respect to this parameterization. So what could that mean? In our framework here, this could mean that, for example, we want to parameterize by the solution size of the problem that we want to solve. And then we design an algorithm that is not solvable, that is not polynomial time, because we don't even expect this to exist, but it's polynomial in terms of the input size and only exponential or whatever that function is in terms of that parameter we picked. And if this parameter is not so big, then that running time is much better than if we have, like up here, if we have up here, if we have the input size in the exponent. So that makes a big difference. But then again, it doesn't always give us everything we want. We still have problem instances that are resistant to, we can't solve them with that. They are too large. They have not nice enough properties to get cracked down fast enough. And so it's great for some problems. It's never completely good enough, but can be great for some problems. But not just that, also not every parameterization of a problem we can find such a fixed parameter algorithm for. It doesn't work. So there are problems, again, we can prove in complexity theory that they are hard for, in terms of parameterized complexity, meaning there's likely no such algorithm existing. So if we look again at our problems I had listed here, then some of these problems, they do have some fixed parameter approaches, and then some of those are actually quite good. In this case here, vertex cover and the max cut problem, they have pretty nice fixed parameter approaches. Vertex cover is the winner, and for matching problems, there are some variants where we have nice parameterizations, and for the TSP problem, I would say there is one, but I would say this is more of theoretical interest than of practical interest at this point. So solving combinatorial optimization problems for best and near optimal solutions is definitely a goal. We don't anticipate that quantum computing will solve every NP-hard problem, just in practical, feasible time optimally. We don't expect that. And for large instances in particular, it will be often infeasible to come up with a guaranteed optimum. Near optimal solutions are also interesting. Otherwise, for example, sometimes you might, because you might be able to come up with your optimum solution, but it would cost you so much more because it takes you so much longer that having a little worse solution might actually be a better trade-off, better in terms of cost effectiveness for the overall application scenario. Also, quantum algorithms are probabilistic, right? And if I calculate or like algorithms can generate these distributions over bit strings, and with higher probabilities, I should get the lower cost solutions. And so if I don't hit the best, I hopefully at least hit something very good. Now, when we want to solve combinatorial optimization problems, then the one step is how do we encode them to solve them quantumly? And one approach is the quantum annealing approach, as used by D-Wave, where they are typically the problems are typically formulated as a quadratic unconstrained binary optimization problem, or QAOA. For QAOA, the quantum approximate optimization algorithm introduced by Fari et al., you can have QBOs, but you also can have higher order binary optimization problems. So you're not constrained only to QBOs. There is this, many of you might have seen it, there's this cool compendium by Lucas on NP-hard problems, and they are described all for all those problems, QBO or Ising formulations for these problems. And just for the people who always heard QBO or always heard Ising, so you can easily hop forth and back from one form to another. That is true for QBO forms, but also for higher order forms. If we want to solve now constrained combinatorial optimization problems, as you just heard, I said the forms that we input into the quantum annealing or the QAOA approach, they are unconstrained, in unconstrained form, they are unconstrained problems. So if we now want to solve constrained problems, there are some approaches that people use. For example, you can describe a constrained combinatorial optimization problem with by an unconstrained binary optimization model using penalties, where you introduce the penalty parameters such that you discourage solutions that violate the constraints. There are other approaches, such as designing circuits that operate for QA that operate within a feasible solution space. But those ones typically require more complex circuitry. So today I want to look at the approach of using the vanilla, that basic QAOA, and how we can tackle constrained combinatorial optimization problems to use QAOA to solve them. And so this is based on work by Priya Angara, who is sitting in our room over there. And yeah, let's get going. So Priya is a PhD student in our group who is actually finishing very soon. So back to QAOA, I do not have time to really get into this in detail, but just a quick refresher, which is almost not needed for the talk. What we, as I said, it is primarily designed to solve unconstrained optimization problems. And it is a discretized gate model friendly version of adiabatic algorithms, if you want to look at it that way. It helps to solve hard optimization problems by first preparing a quantum state and then repeatedly applying two types of operations, namely the one based on a cost Hamiltonian and a mixed Hamiltonian. The cost Hamiltonian encodes the problem, and the mixed Hamiltonian helps us to not get stuck somewhere in a local optimum. And it is a parameterized quantum circuit. That's how it's set up. That uses a classical optimizer to optimize these parameters to maximize or minimize our cost function that we want to calculate. If we would have infinite amount of time, each application of a cost in a mixed Hamiltonian is called a layer. If we would have an infinite amount of layers available, then this would converge to the optimum. So now if we have good parameters, then we hopefully can get away often with shorter running of these circuits. And so this is what using QAOA is about a lot in quantum computing, and see how much we can hopefully improve results and utility in quantum. Okay. So the problem most explored using QAOA is, as I mentioned, is max cut. Mentioned that before. This is what many papers are about. I haven't counted them, but there's a lot of those. And in the meantime, also a few other problems, but max cut is still the go-to one. And so quickly, what is the max cut problem? The max cut problem, we're given, and this now you see the computer science way of describing a problem. We're given a simple undirected graph. And we are looking for what's called a maximum cut. So it means we're actually looking for a subset of vertices such that the number of edges that connect the vertices we selected, here the red ones, to the black ones, the ones we didn't select, the number of edges in between those in this cut, so-called cut, should be maximized. And this problem is an unconstrained problem. And one way to see that is that, so what does the solution look like for maximum cut? It's a subset of vertices that is measured somehow, measured by the cut size, right? So we can do this for every subset. We can look, okay, how many edges are between S, the subset, and the vertices without that subset in the graph. We can do that for everyone. So every selected solution actually lets us calculate the cut size. And because of that, we have an unconstrained problem. We don't have any extra requirements on the solution. So if you want to write max cut as an unconstrained binary optimization form, maybe you want to quickly look at the vector here. So this vector here has an entry for each vertex, vertex 1, vertex 2, vertex 3, etc. And so the selected vertex in S, they are 3, 6, 8, and 10, and these are the ones that are set to 1 here, and all the vertices not selected in S, they are 0 in this example. And so what we're doing now, this is a binary optimization problem, so we are describing now in this formula how to calculate a cut. Namely, what we do is for each edge, we would like to know, are you part of the cut or not? And so this term here, xu plus xv minus 2xu xv, that gives us the value of 1 every time the edge is between the set S and V without S, vertex set without S. And if both of these are, so that is because XU would be selected 1 if it is in S, and 0 if it is not selected in S. And if you, for example, consider the edge 1, 6, and say XU is 1 and XV is 6, XU would be equals 0 because it's not selected. XV would be equals 1 because it is selected, but the term we subtract is 0 because of the value of XU. And so it gives us 1 when that is the case, but if either both XU and XV are set to 1, or if both XU and XV are set to 0, this evaluates to 0. And so this sum here just calculates all the edges in the cut, just counts those. And we are looking for that vector, the assignment of vertices that is best for that. So that's a very nice, brief, clean description of what we have to do to solve this problem. And this is the form we like. This is a QBO. This is the form we like for QAOA. Okay, so max cut is unfortunately one of few unconstrained problems that are used out there. So many problems are constrained. Constraints, I think I see people nodding. So if you work with a problem, typically you might have some constraints it comes with. And so all the ones that are not black here, these are all the ones except max cut of the ones I mentioned, they are, for example, constrained problems. And so one goal is to tackle these constraint problems, and one of our goals is to contribute to quantum utility by adding improved or alternate solutions for solving constrained combinatorial optimization problems with particularly vanilla QAOA at this moment, and contribute with this to benchmarking. And so this here is an IBM benchmarking paper that just came out in April. So if you don't know this, might be worthwhile to check out. So I want to now look at the vertex cover problem. The vertex cover problem you might not all know, but I can introduce it to you. I will do that in a second. But that problem is not just NP-hard. It is a problem that is used for benchmarking in classical computing a lot because it has so many nice properties. There's actually a problem that is, while NP-hard, it's not that bad to solve, but it's something that can tell us a lot. And so vertex cover shows up in many applications. It shows up in conflict resolution and scheduling, to just name a couple. And so many algorithmic approaches can be applied to vertex cover. It's just amazing. You can, for example, there are some approximation algorithms. So to a degree, you can approximate it. There are a lot of fixed parameter techniques that you can use. Almost all the techniques we have for nice algorithms in parameters complexity, you can throw at vertex cover and it will work. And it is used a lot in heuristics and meta heuristics as well, in some backtracking versions, etc. Integer linear programming, you name it. So vertex cover is a great problem to know what it does in quantum, because it has this, for classical, the constraint is not a problem, but for quantum, the constraint, at least for our approaches here, is a little bit of something that we see as a challenge. So what is the vertex cover problem? We're given again an undirected graph, just like before for max cut. Now we are looking for a smallest vertex cover. What is that? It's again a subset of vertices, just like before. Now, every edge in the graph has to be covered, that is a vertex cover. And I show you what this means. And then the set that does that has to be minimized. So we are looking for a subset of vertices. So for example, if I pick these two vertices, they're incident to a number of edges, and these are the edges we cover. So with these two vertices at this point, we are covering all these edges I'm selecting right now. However, this is not yet a vertex cover because they are unselected, uncovered edges, the ones that are not red, right? So this is not a solution for vertex cover, and I'll continue building a vertex cover here, but this is the reason why not every, so this means not every subset that I pick is a vertex cover, and therefore this is a constraint problem. Because the subset of vertices, I don't just look at some measure, like in this case, the size of the vertex cover, I also need it to be a vertex cover. So to complete this example here, to actually have you see a vertex cover, I will continue to pick some vertices, and I'm promising you I'm actually picking a minimum vertex cover in this case here. And they are covering those additional edges, and I'm actually still not completely done. I still have 2 more vertices I need to include. Chose these 2 here, and now all edges are covered. So in this case here, these 2, 4, 6 vertices, I believe, they are needed to cover all the edges in the graph. So the problem is, in general, to find a smallest set of vertices that covers the whole graph, all those edges in the graph. And again, as before, I described the set we chose by a binary vector, just the same way, the vertices enumerated from 1 to 10. And if I now want to write vertex cover as an unconstrained binary optimization form problem, then what do we do? Just counting the vertices, that's what this term here does, isn't enough. So what we need to make sure, we need to discourage solutions that are no vertex covers. And that's what we do by introducing this term here and using a penalty. So this term here penalizes every uncovered edge in the graph, right? In this graph, we don't have that. So this should evaluate to 0. But if we have uncovered edges, then they would be caught here. Why is that? Well, if I have an edge that is not covered, that means that both XU and XV are set to 0. But that means that I have here 1 times 1 sitting here. And so for each edge that is uncovered, I will add A to my cost here. Now, that is a cool idea, and that is not bad. If I'm interested only in the optimum to solve vertex cover, then actually this does the trick, because best solutions are maintained as long as I choose A larger than B. That works out. But it does give me trouble to find near optimum solutions. So in this little example here, granted it's just a very small example, but comes out better in larger instances. But this one here is our vertex cover, and using this formula for A equals 3 and B equals 2, if you have 2 times 4 for the number of vertices in the cover, plus 0, so that evaluates to 8. And I promise you this is the minimum vertex cover, so this is the best we can get here. So this is 8. If we have instead an incomplete vertex cover, for example, these 3 vertices, then these 3 vertices here, they evaluate with B equals 2 to 6. And then we have this uncovered edge, and the uncovered edge makes me add A. And if I add A equals 3 to it, then I get 9. Now, that is not a good thing because there are other vertex covers in there. So this is not my second best vertex cover, but this is my second best cost I get by setting these penalties like that. Now you could say, well, why don't I just set the penalties better? And yes, you can do that for each individual instance. You can find better penalties to do a good job, but you have to do this for each instance really. Or, you know, maybe there's some way for certain types of graphs, these type of penalties might turn out to be pretty good, but this is a hard problem by itself. So the choice of penalties to support near optimum solutions is graph dependent, or in general instance dependent. And that is one of the problems with this approach. So, well, if we have a problem with constrained problems, can we maybe utilize unconstrained problems to help us solve these constrained problems? So this is an approach that Priya is using. And so constrained combinatorial optimization problem, if I have one, I would like to somehow do something to the problem by getting rid of the constraint, but I can't get rid of everything, right? I still want to solve this problem in the end. Sophisticated way of solving this problem. So, but let's assume I have an unconstrained combinatorial optimization problem that I can write up as a nice unconstrained, QBO or HUBO, and then solve that using QAOA. I'm getting a solution out that is, say, near optimal for this PU, for this unconstrained optimization problem. Now, it may already turn out accidentally to be also a solution for that. And if I have done things right, then it will be a high quality for this one here. It may be not one. And then what I want is I want to be able to create a solution for the constraint problem by some effective post-processing. Now, very important is what we are doing here, getting this problem and the relationship between these two problems and the post-processing. This needs to ensure that I have a solution quality for this original problem. Okay. So for vertex cover, there is actually a problem out there, the problem profit cover, created for different reasons long time ago. And profit cover, again, sorry for that, but the third graph problem I'm introducing to you here. Profit cover, again, has a simple undirected graph as input. And now I'm looking for a maximum profit cover. What is this? So it's now a maximization problem. I'm looking again for a subset of vertices, and the subset of vertices I want to evaluate with respect to its profit. The profit is defined to be the number of edges covered by the set that I picked minus the size of the set. So in this case here, if I pick these 4 vertices that, by the way, are vertex cover, every edge is red, then the profit is calculated by counting all these edges. These are 10 minus the 4 vertices in the vertex cover. So the profit we get here is 6. Now, this here is also a subset where I can evaluate the profit for. So this is actually an unconstrained problem because of that. I can do this for any subset. And if I calculate how many edges are covered, not all of them are, but 9 of them are, minus the vertices spent. So this is also a profit of 6. So with respect to profit cover, these two solutions are equally good.
Can I ask a question?
Sure, Rogerio.
Is this by any chance a Lagrange multiplier? You know, when you minimize subtraction.
I would say the answer is no. We can talk about it later more.
Okay, because in math, when we want to map a constraint problem into a constraint problem, we use Lagrange multiplier.
You do, yeah. So direct mapping, and I'm not sure I understand you correctly. So maybe we table it for a little bit for later. But I think I know what you mean, and I think the answer is no. But we can talk about it in more detail later. Okay. All right. So we have as I said, we have here an unconstrained problem, which is nice. And of course, we want this unconstrained problem to do the job that I outlined before. Now, we can write up profit cover as an unconstrained binary optimization problem without any penalties. And so these are the edges covered, what is summed here. And these are the vertices that we spent to cover it. Don't want to go through the details again right now of the formula because I think of the time constraints. But what we know is that there is this nice relationship between this profit cover problem and the vertex cover problem. Namely, if I have a vertex cover of particular size, then I can come up with a profit cover of size number of edges minus the vertex cover size, and vice versa. If I have a profit cover of particular profit, I can come up with a vertex cover of adverse that size of the number of edges minus that profit. And that relationship is one cool thing, but it also, at the same time, these problems allow us to take any solution for profit cover where we know the profit of that is not a vertex cover, we can, without decreasing the profit. So we might improve the profit, we might keep it the same. We can determine a vertex cover for it. And that vertex cover, we know the quality of it. It is a comparative quality. So what we basically have is we have potentially a few more solutions in profit cover that give us additionally good results. But from these, we can derive vertex cover solutions. So in particular, for a high probability solution for profit cover obtained using our approach with QAOA, that will correspond to a high quality solution for profit cover, and could also be right away a high quality solution for vertex cover. And if not, that means it's not a vertex cover. That means we can then effectively post-process with a linear running time to get a feasible solution for vertex cover out of it. So in this case here, we could just add a vertex, one of these two vertices to cover this edge, for example. Okay, so Priya generalized or figured out the properties that such a twin of problems, a constrained and an unconstrained problem, need to, or if they satisfy these properties, then we are having a good scenario where we can actually use an unconstrained problem to solve the constrained one. And so these properties are based on, they have to have the same input domain. The solutions have to be of the same form, meaning every solution, like a subset of vertices for the constrained problem, is right away a solution for the unconstrained problem. The objective functions, they have to be compatible in the sense that we can we know what a value in the one problem means for a value in the other problem when we calculate it, and we need to be able to efficiently come up with a, be able to update a solution that doesn't satisfy the constraint of the original problem. So the framework consists of these of identifying these properties and then a strategy how one could derive potential candidates, unconstrained problems for a particular constrained problem that satisfies these properties. And so it turns out there are a few more problems out there that are unconstrained twins to famous constrained NP-hard problems out there. This is for independent set and clique and dominating set in addition to vertex cover. And so Priya showed all of these being what we call goop twins, and also could derive for the set cover problem, and I haven't introduced those problems to you, so feel free to look them up, and several matching problems as also a unconstrained twin. Now, for independent set, vertex cover, and clique, we have QBOs for the unconstrained problem. For the other problems, we have higher order terms. So what does this framework give us? It gives us a hybrid quantum classical strategy to solve constrained combinatorial optimization problems for all those problems where the scoop framework applies. And it will give us a catalog of relevant unconstrained problems to work with, in addition to, for example, MaxCut. And it will allow us to do more benchmarking. We can investigate scalability much better for that. Constraint problems, it's a bit of a struggle, the interpretation of the results, etc. And so we also have now unconstrained HUBOs, which are, well, first of all, they can be all transformed into QBOs by adding penalties again. If you need a QBO, you must introduce penalties if you can't describe it by a QBO directly. However, you have at least less penalties than before because for the constraints, we got rid of those. And also, it gives us, for working with QAOA, it gives us some extra opportunity to work with HUBOs directly. If the terms are not too high, there is some success of implementing those. And yeah, was suggested also before that this might be actually a good idea to do so by Campbell and colleagues. And Priya has, for the dominating set problem, for those unconstrained version, she has implemented this successfully for 3 regular graphs. How am I with time? Still a little bit of time. Okay, so I brought here a little bit of experimental results that we got from the work. This is on simulators for, okay, simulation were done on penny lane and on QTensor, and the results I brought here are all on small graphs. But in the papers that I had in the earlier slide, you can see more of the experimental results, and this is all on profit cover and vertex cover. So we used penny lane for full state vector simulation to see what's going on, but that only works for the small graphs, and for the larger graphs, we used Argon's QTensor. So here you see a comparison of vertex cover for 3 different penalty settings for this little graph here. You can't really show a full state vector simulation with more than a tiny graph. And the profit cover approach, so these are the blue ones here, and you see that they are quite different between the different penalties. What the probabilities are for this, these are all the states, right? And the states here, these 3 are the top results, the optimum results for the profit cover solution, and the 2 blue ones are in addition also the best vertex cover solution. So the orange one is profit cover run, just as it comes. And the dark red one is profit cover post-process to vertex cover solution. So if we want to actually see what the combination is, what are the probabilities then? And you can see that the approach raises up the probability nicely in this case. So depending on your penalties, running vertex cover might not be so bad, but depending on your penalties, it might be. And so profit cover gives you, just like MaxCut, more reliable results. I think I'm starting to run out of time. So we have here comparison of vertex cover and profit cover with the summed probability metric, which makes it compared to some other metrics a little bit easier to compare a constrained and unconstrained problem, because the constrained problems are actually difficult to evaluate. That's one of the issues. Okay. And so these are best. This is for best solutions. This is 8 layers on the QAOA, and then we have second best and third best, and you can see how the performance of profit cover, which is the blue line, improves. Also, approximation ratio is one of those metrics that doesn't work so well for constrained problems. This one can now be used using the unconstrained twins. And yeah, I think you saw the idea how this work might be able to contribute to quantum utility. But let me just briefly mention a little bit of other things that are going on in our group. So, for example, my student Tristan Zaborniak, he also works on constrained combinatorial optimization problems in QBOs. He does it from a different angle. He really wants QBOs because he works with the annealing approach. And so he investigates different encodings and properties for discrete quadratic models, among other things. And he is working in particular on problems from computation biomolecular structure problems like RNA secondary structure, protein design, etc. We have a team of great master's students. Juan already defended, Jose, who's defending. When is it? In 2 days? Thursday. So they out of their work, there is this library Qplex that is kind of, if you know Cplex, then this is what Qplex is, just including quantum. It's a library for modeling and solving combinatorial optimization problems through different classical and quantum, quantum computing resources. And so what it allows, well, of course, you can expand it later on. It is, I can give you the GitHub in a moment, but the Qplex works with an abstraction layer where you can propagate to Qiskit Ocean or Bracket and then connect with the different providers. So it's a nice experimental platform, but also you can actually get into this layer here if need be and fine-tune things. And so this is the GitHub for this. And we also have a paper and Quantum Week for that. It was from 23. That's the archive link here. Okay, so what else is going on? There is a lot of quantum computing learning tool design and education, quantum education in our group. Samantha, who's sitting here, is one of the main authors. She is part of 3 of these, and Jose, you just heard about, he is part of the quantum crypto tool. So the quantum crypto tool, don't have time, I think, to talk about it much, but you can check it out. Here's the website, and Q notation is also a notation while in between, again under construction, because Qiskit just changed to Qiskit 2.0, for example. It is up and running, and if you want to play with it, go for it and let us know. Connect with Samantha and let us know how that's going. And so, yes, so we also have from a former master student, we have a visualization tool for quantum walks to make these more accessible. And there's also a nice visualization tool on the Grover algorithm by Samantha. Okay, so this is a thank you to the amazing group and collaborators. And I know I didn't list everyone, but I listed hopefully all the students who have recently graduated in quantum. There are also a couple of other PhD students in my group on here, and some of our collaborators for the work I was talking about Priya's work. We have an amazing undergrad who contributed to it. And with that, I want to finish with this last slide. This is what we are up to right now. We are in a bunch of projects, just like, for example, Housie sitting over there. There's this big grant for distributed quantum computing, an Answer Quantum Alliance grant. And I have a Quantum Alliance grant, 3-year project for quantum computing for optimal mobility with TMU. And yeah, maybe one more thing. There is this cool conference, Quantum Week. Here are the dates. If you have never heard about it, click it. If you heard about it, be reminded that you can attend in person, but also hybrid. And it has been amazing last year, and expecting the program this year to be just as good. Okay, thank you.
Thank you for that talk. That was a very nice overview of optimization problems. We hear someone talk about this for a while. So, it doesn't have to be a local question, but do we have a question online or here or?
Here is a question. Jeff has a question. Please.
First of all, thank you so much for the talk. Could you go back to the slide where you kind of showed the plot of post-processing with profit covers? I was just curious, what did you mean by layers equals 3?
You mean the experiments?
Yeah, here, 3 layers. What do you mean by that?
Oh, these were 3 layers of QAOA. So 3 times the cost in the mixer Hamiltonian repeated, basically.
I see. Okay, thank you.
So the longer the circuit, the tougher that is nowadays. So if you can get good results with just a few of those, that's nice. But overall, results improve if everything goes, on the simulator. If you are able to run them longer, but depending on the size, etc., that's a trade-off.
Can you show the circle?
The picture there? I don't know how. Well, that was just a sketch here, right? There's disclaimer of some sketch grab from some of old stuff and here.
Yeah, exactly. The number of yellow boxes, right? That's what you mean by layers.
Yes, yellow, orange. So one yellow, orange is 1 layer. So cost and mixer Hamiltonian. Cost and mixer Hamiltonian, second layer, etc. Yeah, that's right. And if you would have an infinite amount here, then life would be really cool. Yeah.
Can I ask a follow-up question on this? So what is the time to solution of this algorithm, of this QAOA algorithm? Is it known? Like how does it scale with the number of qubits?
Do we know that, how it scales with the number of qubits? It depends a lot also on the gates, meaning on the cost Hamiltonian, etc. What you're using, it's all dependent on that. So this is not general. It's problem specific, right? It's depending on the problem. You have a way more complex or easier situation there.
So it's not like Shor's algorithm where you have a clear order of analog and
No, have you ever seen that? I've never seen that.
I
No.
think he's asking what the computational complexity.
Complexity of QAOA. I mean,
if
you
there is
run
instances that are-
infinite amount of layers if you can, right? So there it blows up, but it's what really is important that you have a nice clean short circuit if you can for the cost and the mixer Hamiltonian to implement that.
So yeah, this is what I thought, because I've never seen, the time to solution, a formula for the time to solution QAOA. I think it doesn't exist.
Yeah, I can't answer that. Yeah.
That's why it's called Approximate.
Well, no.
I mean, the other
add more layers based on it.
okay, but
I think Priya has a comment, right?
Yeah, I mean, if QAOA is not solving one problem,
No.
solving you can
Any.
use any combinatorial optimization, right? So you cannot comment on the time to solution the results.
It doesn't just depend on the number of qubits. Yeah.
Problem you have, and then at the end, the result that you get, that's also as how we said, it's optimization algorithm. So the more layers you have, the better your solution is. But again, on simulators, that's fine, but on real hardware, you have maybe many layers, but then your error rates are going to go up. And then it's also dependent on the graph, because if you have a very dense graph, then you have a lot more gates in that e to the I gamma H field. So because too many connections.
So the reason why I'm asking is because, how do we know this has any speed up in comparison to a classical algorithm?
Well, right now, what am I interested in? I'm not necessarily interested in that. I'm interested to getting right now, we are still waiting for the good enough powerful computers to do that. But I'm hoping that this scales to at least get beyond what we can do right now classically, so that we have a bunch of NP-hard problems where we can get better solutions to instances that we can't do before, where we can push those limits. So this is really what I'm interested in at this moment, because I do not expect that we can solve these problems in polynomial time. There is generally, nobody expects that P equals NP in the quantum world is basically diminished. That question, that's still there. So it's really about, helping us to solve problems. Faster, smarter is an alternative method, and it's an approximation, and it's not a guaranteed speed up for anything. This is not what this is about. For that, you would have to look at a particular algorithm, develop a quantum algorithm directly, for example, etc. And this is not what this is about. Yeah.
No, I fully understand. And in fact, I will point out that it's similar to quantum annealing. No one has any handle.
Yeah, except that, the difference is that if the quantum computers, gate-based quantum computers have potentially more power to solve more problems on that, but it is definitely comparable in this. We have the handle of how we solve the algorithm in quantum annealing, and we pop in that QAOA. And here we have a bit more we can pop in basically, but and then we run this thing, and those things are very comparable. Absolutely, yeah.
Thank you.
I think we have a question online.
Yes, please. I think that was.
Hi, Ulrike, thanks for a nice talk. So I'm just curious, in the practice couple problem you mentioned, do you encounter any example that have any quantum advantage in whatever definition?
I'm not sure. Can you repeat the question? I couldn't.
He wants to know if you encounter any problem that has a quantum advantage in any definition, or I suppose quantum utility would also do this.
Of those NP-hard problems, no. I only know what's known from the literature that has a provable quantum speed up. Let's say it like this, right? So there's a debate between, speed up and advantage and utility, etc. But no, I don't.
Thanks.
Well, that's all the questions.
I have another question. So my other comment is that, I mean, of course, we know that the D-wave quantum annealer is a native max cut, right? So, in a way, it's kind of it doesn't have any overhead that you have here. So, it would be interesting to also use the D-wave quantum annealer to benchmark this, right?
Absolutely, I agree.
Because I mean, it sounds like, comparing quantum annealing to this, that this is much more complicated than the circuits are very complicated. Right? I mean, quantum annealing is basically.
I'm not an expert in quantum annealing, but I can tell you that I agree. I would like in the future that we get the opportunity to try out some of these unconstrained problems that we have now, particularly the ones that are natively a QAOA, to solve them there and see what happens, see how they do. Absolutely, that's very interesting and should definitely be done. Yeah.
I think this is more general than max cut, right? You can solve other problems other than max cut with this.
QAOA is for any problem that you can bring in the right form. Absolutely, yeah.
Go to the chair. If this is it, then thank you.
Thank you, Thomas. Thanks so much.
Oh, thank you.
Thank you.
You.
Okay, then I'm.
Thanks for the talk.